An 18-turn coil encloses an elliptical area having a major axis of 40 centimeters and a minor axis of 30 centimeters. The coil lies in the plane of the page and carries a clockwise current of 6 amps. If the coil is in a uniform magnetic field of 2 times 10 to the minus 4 Tesla directed toward the left of the page, what is the magnitude of the torque on the coil? Okay, so big question right now is, how do we calculate the torque acting on a current carrying coil of wire? Well, we have learned in this chapter that that torque, that magnitude of torque, is going to equal the magnitude of the magnetic field multiplied by the current flowing through the coil, multiplied by the area of the coil, multiplied by the number of turns in the coil, and then multiplied by the sine of an angle. And we're going to talk about what that angle is very soon. So we look back at the given information, and some of this is given quite directly. So for example, the magnetic field magnitude is listed right here, so we can jot that down. The current that's flowing through the coil is also given directly. It's 6 amps, so that's included in our list of knowns. Where things might get a little tricky is determining the area of this elliptical coil right here. So luckily they have given us a hint. They say that the area of this ellipse is going to equal pi times A times B. Now be careful here, because A and B are the semi-major and semi-minor axes. The emphasis here is on semi. And if you look back at the picture, we were not given the lengths of the semi-major and semi-minor. We were given the lengths of the major and the minor axes. So in other words, this 40 centimeters is the major axis, but we need the semi-major, and as you might guess, the semi-major axis is obtained by just dividing the major axis by 2. So we're going to go ahead and we're going to say that little a is equal to 40 centimeters divided by 2. So just make sure that you divide that by 2. That's going to give you 20 centimeters. Now we need that in a standard unit, so let's make a little bit of room here. We need it in meters. So basically, you just divide the 20 centimeters by 100, because there's 100 centimeters in a meter, and you're going to get 0.20. So we'll just make a little refinement right here, actually, and it'll be 0.20 meters. Now for little b, we take the length of the minor axis right here and divide that by 2. So that's just going to be 15 centimeters. Divide that by 100, and you get 0.15 meters. So now we would be able to find the area, because they told us how to. They said that it's pi times A times B. So we're going to take pi, multiply that by 0.2 meters, and then multiply that by 0.15 meters. Now maybe what we'll do is just leave it in terms of pi. So we'll just multiply 0.2 by 0.15. We get 0.03 pi. 0.03 pi. We multiplied meters by meters, so we have meters squared. Okay, so we have the magnetic field, the current, and the area. We also need N, which is the number of turns in this coil, but that was directly given to us right there. So we do know that N is equal to 8. The only other piece of data we need is the angle. So let's talk about that angle. It's going to be an angle between the magnetic field and a line that runs through the center of the loop. Now the perspective of this drawing is a little bit tricky, so you might want to pause and think about what that angle is, but here is the line, an imaginary line, that runs through the center of the loop, and then we have the magnetic field pointing to the left. Now I'm going to skew it just a little bit. I know that's not directly to the left, but this would be the correct perspective, because when we draw it that way, we can see that the angle between that line going through the center of the loop and the magnetic field direction is 90 degrees. So theta is going to equal 90 degrees. Now we have all of the data that we need to plug in to our torque formula. So we're just going to scoot down the page and plug everything in. And when we do that, we will see that the magnitude of the torque on this coil is roughly 9.05 times 10 to the minus 4, and the standard unit of torque is a Newton meter. So this would be the correct answer to this question.